My presentation today is about the lightning core voltage analysis applied for a 500 kV substation. This is an interesting example, interesting case study, so I just wanted to share this in this user meeting. So the agenda is that I will start with the introduction and problem statement. Then I will try briefly describe the methodology used in the study, then some modeling details, then simulations and conclusions from these simulations. Firstly, let me say that I have reviewed many lightning overvoltage analysis reports in my career. And what I have noticed is that the methodologies used in different reports were completely different, especially in the definition of the main parameters for the study and modeling the system. In this presentation, I will try to focus on the main parameters that would affect the result of this overvoltage analysis, which I think the most important parameter is the lightning flash modeling. So I will try to focus specifically on lightning flash modeling. Okay, about the introduction. In this case study, we had a 500 kV substation where the surge arrestor was placed quite close to the auto transformer. This is a 500 kV to 220 kV auto transformer with 11 kV tertiary winding. Physically, it's quite close, around 10 meters from the surge arrestor to the bushing of the transformer. But due to the tertiary winding bus bar of this transformer, it was not possible to make a direct connection from the surge arrestor to the bushing of the auto transformer, 500 kV bushing of the auto transformer. So there had to be a riser conductor, then a parallel path and a down conductor to the bushing, which would give a total of around 40 meters of electrical distance. So the question was that if the placement of the surge arrestor is correct, considering this 40 meters of electrical distance. For lower frequency, let's say, that is slow front over voltages, the distance may not be an issue, like switching over voltages, that 40 meters, whether it's 5 meters or 40 meters, it will not make an important difference considering the over voltage levels. But for lightning over voltage analysis, due to its high frequency content, the voltage buildup on the conductor in between the surge arrestor and auto transformer bushing may be important to affect the insulation properties of the system. Therefore, insulation parameters of the system. Therefore, we decided to check if the placement was adequate, considering the lightning over voltages. Therefore, this analysis was limited to lightning over voltages only. Yes, here is a very brief description of the methodology we have followed. The first assumption is, of course, that the path of lightning over voltage invasion to the substation would be from the overhead line, because we don't expect any lightning to terminate on line conductors inside the substation because of the lightning protection measures taken for every substation. So we consider that lightning surge can propagate to the substation only from overhead line. And as it is very well known, a lightning strike can affect an overhead line in 3 ways. The first one is induced over voltage. This is more related to the distribution level, so it's not our case. So back flashovers and shielding failures are considered in this case study. And the procedure for the study is that, firstly, we specified we modeled the lightning flash, which is probably the most important parameter of an analysis. Then we modeled the other components like tower, surge arrestor, conductor, HV apparatus, etc. Then we applied simulations using EMTP. Then we evaluated the results of the simulation. Okay, the first thing for having such a case study is to define the representative lightning flashes to be used in the simulation. When you go to different sources like standards, like technical brochures of CIGRE, or like example reports from some reference companies in the market, you may notice that the parameters used for the lightning flashes differ considerably. So I had to go through many references to find an acceptable reference to follow all along the case study. And we decided to use CIGRE Technical Brochure 63, which was upgraded in 2021 very recently. So most of the parameters or most of the recommendations, most of the selections in this case study was based on the recommendations given in CIGRE Technical Brochure 63. Lightning flash model depend on several main parameters like downward, upward flash, positive, negative flash, or return stroke, or subsequent stroke, or wave shape. So, and I think the first step to define a wave shape is to decide which main parameters to be used in the analysis. So in this selection, we have followed the recommendations provided by CIGRE. For example, in downward and upward flash, as it's well known, upward flashes occur mainly from very tall structures, much taller than transmission line towers. Therefore, only downward flashes were considered in this study. Similarly, positive and negative flashes, a lightning flash can be a positive or negative one. But according to the related literature, positive flashes are experienced typically 10% or less. Therefore, we have selected negative flashes. We have considered negative flashes, which are more prevalent in comparison to the positive ones. And of course, a lightning flash may have several strokes. That is the first stroke, that's the return stroke, and subsequent strokes. But according to related literature, the amplitude of subsequent strokes tend to be significantly lower than the first one. Therefore, we have considered the first stroke only, that's the return stroke only. So these were the main recommendations given in CIGRE Technical Brochure. The next step for the selection of or modeling of the lightning flash is to select the wave shape. This can be either a CIGRE concave wave shape as offered in the CIGRE Technical Brochure, or a double ramp, IEEE double ramp shape, which is used by IEEE, by the way. But according to IEC 60071-4, it is recommended to use CIGRE concave shape, which is suggested to give more realistic results. So we have selected this one. So as a summary, we have selected a lightning flash wave shape of CIGRE concave shape with downward negative first stroke modeling. So let's very briefly review how we select the parameter, or how we calculate the parameters of this selected wave shape. A CIGRE concave wave shape, as you can see on the right bottom side, can be modeled with mainly 4 parameters. That is the crest current IF value, the maximum front stiffness SM, time to crest value TF or TD30, which is equal to T30 divided by 0.6, and time to half value. And also it's very known that lightning parameters are specified statistically. So the first thing to do when calculating these parameters is to calculate firstly the crest current value, IF and IF value for back flashover and shielding failure cases. Once this IF value is calculated, then derived parameters or derived distributions of steepness and front time can be calculated using the table provided in CIGRE technical brochure 63. That is, you can see on the right side. So I just put here a summary of the parameters used in the simulation for back flashover cases and shielding failure cases. That front time and steepness is calculated based on the value selected for the crest current of back flashovers and shielding failures. By the way, this usage of median values are also recommended in CIGRE brochure. On the other hand, the fourth parameter, that is the time to half value, is not very critical in such analysis. So a median value of 77.5 microsecond is used in all simulations. Okay, as we said, the crest current, the definition of or calculation of crest current is important for the lightning flash modeling. So this value is dependent on whether it's a back flashover case or shielding failure case. For back flashover case, I will try to very briefly describe the process or procedure that we followed for calculating the crest current. As it is known, when a lightning strikes to a transmission line tower and passes through the tower to the ground, and there is a voltage buildup on the tower. So the tower attains a high potential in comparison to the ground, while the power line, that's the line conductor, is not very much affected with this lightning strike. Therefore, there happens to be a voltage difference between the line conductor and the normally grounded or normally at zero potential transmission line tower, which attains a very high potential in case of a lightning strike. And if the potential difference between these two becomes higher than the withstand capability of the insulator, then there happens back flashover. And this back flashover, the possibility of this back flashover is directly related to the lightning crest current value, not maybe directly related, but let's say increasing lightning crest current increases the possibility of back flashover. On the other hand, it's not economically viable to design a system which would withstand any possible lightning crest value because it would be economically nonsense. Then it is logical to specify an acceptable failure rate, which is already specified in IEC standard, which is between once in a 250 years and once in a 1000 years. So if the failure is in between these values, then it is accepted. So the selection of the crest current is based on a very simple criteria. If the probability of exceeding a selected crest current value is lower than the acceptable failure rate, then this current level is acceptable. That is, if a substation equipment can withstand this value, it's acceptable even if they fail for any current over this value, because we know that its possibility is quite low or acceptable. So the process is iterative. The first thing is to select the crest current, which is maximum 200 kiloamps. Then calculate the probability of exceeding this value. If it is out of range, then go to the next step. Okay. The probability of exceeding this selected crest current value is related to number of overhead lines, of course, and number of flashes to exposed area, that's NG value, and the probability of lightning current. As it is known, probability of lightning current is log norm is given with a log normal distribution. So for any selected current, crest current value, it's possible to calculate the probability value, probability function. Number of overhead lines can be easily specified. Then the number of flashes to the exposed area, that's the NG, which is related to the ground flash density, which is related to the Caronic level. That's a geographical parameter. Then the exposed width of the overhead line, which is again related to the geometry of the tower. That's the distance between shield wires and attractive radius of the shield wires, and the limit overhead line distance. So I think the most tricky parameter here is the XP value, that's the limit overhead line, which is basically the section of overhead line to be considered in the analysis. So this selection can be either iterative or it may be based on very simple assumptions. If it is an iterative solution selection is used, then a maximum value of 200 kilo can be selected. Then with simulation, the distance XP, which would not result in a failure in the substation equipment, can be found. Then IF value, crest current value, can be calculated with this XP. Then this current value can be used again for calculating the new XP value. Then iteration continues until the values, the process converges to an acceptable XP value. Or another solution is to use the minimum limit overhead line distance given in the IC standard as 2.5 span of overhead line. In this case study, we have tried both of these selections, and we have used the minimum value, which turned out to be larger than the iterative value find from the iterative solution. So we used 2.5 span of overhead line. Okay, and about the shielding failure. The shielding failure is about low level of lightning currents. As you can see on the graph on the right side, the attractive radiuses or striking distances of conductors are related to the crest current of the lightning. Therefore, for lightning current, very low levels of lightning, there happens to be a arc DC where the lightning step leader would terminate in the line conductor instead of the shield wire. So as the current increases, as the current of the lightning flash increases, that arc DC diminishes. Therefore, after a value, there is no possibility of having a strike to the line conductor. So the process is quite simple here with the very well-known representations or formulas. It's possible to calculate the maximum current for the shielding, expected level of shielding failure cases. And once this maximum value of the crest current is calculated, then we can simulate to see if really results in a failure in the substation. Okay, this was all about the lightning flash modeling, which I believe is quite important for the modeling of for the simulation of the system, because this is really the main parameter. If this parameter is selected inappropriately, let's say, then the result would be may not be useful at all. Okay, then the remaining parts of the modeling, let me go through it very shortly. The tower model, since it is a 500 kV substation, 500 kV system, the tower was a large one, so a multi-story parameter model is implemented, which is given in IC 60071, and this model is is applicable for the main body of the tower. So cross arms needs to be calculated with a lumped inductive element for 1 microhenry per meter. And the parameters of this multi-story model is calculated, in our case at least, based on a paper by Ametani which I have given the reference in the presentation. And the tower footing resistance is modeled with soil ionization. That is the one when there is a ionized soil, then the tower footing resistance becomes lower, decreases. So it is already available in the typical examples in EMTP. So we followed the example, the model given in the example 5. The second item related to tower is of course, the line insulator. There are many models. There are many models to use for line insulator modeling, but we have selected the most simple one. That's the voltage controlled ideal switch, which is based on a very simple calculation based on the air gap distance. In fact, maybe in the future we can try some further methodologies to model the line insulator. And surge arresters, modeling of surge arresters, we have used the methodology specified by IEEE Working Group 3411. There is a very good training in EMTP website, EMTP YouTube channel about this modeling methodology, and also some very good examples in EMTP library. So we have used those to model our surge arresters accordingly. And other modeling considerations. For overhead lines, we have used frequency-dependent line model. We can use wideband model as well. We have checked that there is no significant difference between these two, so we use frequency-dependent model. Tubular bus bars of the substations, because as the span of the feeder, width of the feeder is very large, the tubular bus bars becomes important. So we modeled the tubular bus bars with the frequency-dependent line model again. And the short conductors between high voltage apparatus, that's between current transformer to circuit breaker, for example, we have used a constant parameter line model with 1 milliohm resistance, characteristic impedance of 250 ohms with velocity of speed of light. And all other short connections like down conductors from surge arresters, for example, we use the lump inductance of 1 microhenry per meter. And for other HV apparatus like circuit breaker, disconnect switches, CTVT, and of course the transformer or reactor, we modeled these apparatus with capacitances, and these capacitance values were taken from manufacturer data when available. When they are not available, we have referred to the IC 60071-4 recommendations. So in the end, here is our model. We have modeled the system up to 200 kilometers, 2 kilometers. Then we have added 100 kilometers of line section in order to avoid reflections, of course. Then here, in fact, it's a 500 to 220 kV substations. So we have a 220 kV side as well. Here is the diameter of 500 kV substation. That's the line entrance and outgoing for the auto transformer. Also, we had another connection in another diameter to a reactor where we have measured the simulated voltage waveforms as well. And here is the auto transformer, and here is the surge arrestor, which is the subject of this case study. So basically, what we are doing is that we are checking the voltage on auto transformer terminals, which is 40 meters away from the surge arrestor, and check if it is if the voltage level is acceptable or not. So we have specified mainly 4 cases, 2 for 500 kV and 2 for 220 kV. For the purpose of this presentation, we present only 500 kV part. The case 1 is the back flashover case, and case 2 is the shielding failure case. And before going further into the simulations, we need to specify the acceptable level of overvoltages for the auto transformer or for any high voltage apparatus. So, of course, it would not be logical to use the maximum acceptable value for the apparatus, that's the lightning impulse with descent voltage level, then it should be divided by a safety margin as specified in IEC. This value is given as recommended as 1.15, so we have followed this value. Then the lightning impulse with descent voltage level of 1,550 kilovolt divided by 115 gives us 1,348 kilovolt, which is the maximum acceptable limit value for the overvoltage on any apparatus terminal. So the first simulation was the back flashover analysis for 500 kV. As we have described the calculation methodology for the back flashover waveform, the result for that analysis was that the crest current is 150 kiloamps with a steepness of 44.8 kiloamps per microsecond and with a front time of 7.5 microsecond. When we apply this lightning surge to the first, second, third towers of interest in the area of interest, I mean, of the line section, we didn't observe any back flashovers on the insulators. As you can see here, this is the overvoltage on the tower and the overvoltage on the line conductors, phase A, phase B, and phase C, just nearby the tower. And on the right side, you can see the current through the voltage control switches of the insulator, modeled insulator. As you see, there is no flashover with the calculated parameters for back flashover. Then we can say that we don't expect any back flashover, so there is no issue about the back flashover case. In fact, we can just skip this value, skip this case for back flashover case, back flashover analysis. This is quite in line with the literature, by the way. This is also specified in the, as far as I remember, the book of Hilleman as well. So at 500 kV level, the strength of the insulators are so high that you don't really expect any flashover for lightning cases. But in this case, at least we have seen this by ourselves as well. In order to see what happens if somehow we have an overvoltage, we have a back flashover, we tried to decrease the front time, as the decrease of the front time would result in a much higher back flashover possibility. So we decreased the front time from 7.1 to 3 microsecond. Then with this value, we achieved a flashover on phase C, which is the outermost, lowermost phase on the tower. And the maximum voltage on the auto-transformer bushing has been measured as 1098 kilowatt, which is quite lower than the acceptable level. And we have tried to change the source phase angle in order to see its effect, because it really affects the actual position of the voltage on the line conductor would normally affect the voltage difference against the insulated terminals. So we changed the source phase angle to see its effect, but the result, we didn't have any higher result than the 1098 kilowatt. So we can safely say that the expected maximum overvoltage on the transformer bushing is 1098 kilowatt, which is lower than the acceptable value. So this is the result of the back flashover analysis. Even somehow we come across, we encounter experience or back flashover, that would not harm our transformer. That's the main idea of the case analysis. Then the second case is the shielding failure analysis. With the calculation methodology we presented in previous pages, the crest current was calculated as 17 kiloamps. The steepness of the waveform was calculated as 19.5 kiloamps per microsecond, and front time was 3 microsecond. When we apply this waveform, lightning waveform, to phase A, the simulated or measured over voltages on substation gantry and auto transformer bushing were 1092 kilovolt and 1020 kilovolts respectively, which are quite lower than the maximum acceptable level of overvoltage. And we have changed the stricken phase from A to C, which are the outermost phases, and this change did not result in any higher voltage in auto transformer bushing, so we can conclude that the expected maximum shielding failure or voltage level would be quite lower than the maximum acceptable value. So the conclusion is that this lightning over voltage analysis conducted have shown that both for backflash over cases and shielding failure cases, the expected over voltages, maximum over voltages, are lower than the tolerable values. So we have decided that the placement and rating of surge arresters used for the auto transformer protection would provide necessary protection to the transformer, even in this quite strange application, having quite a long electrical distance between the surge arrestor and the auto transformer. And here are the references. So thank you for listening, and I would be happy to answer any question if I know the answer.